This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So mobile. So then it's you don't no longer need to make this surface flat. It can be curved, so you can make more congruent types of surfaces. So that's probably the last thing I just wanted to mention was how do we assess these designs. So one aspect that's required by the regulating bodies is experiments, and they might. One very common one is a wear test. So they'll actually take a joint and articulate it, 20 years worth of articulation and measure how much wear it actually undergoes. All right, so I'll go straight on to the next lecture. Were there any questions with that at all? Right, so this lecture's mainly focused on fracture fixation. So the other ones were joint replacements, but fracture fixation. So fracture fixation is used to stabilise fractures, and there's lots of different ways you can do it. So you can, if a patient breaks a bone through, say a car accident, fall, or osteoporosis, for an adult they usually do, depends on how bad the break is, but they can often need surgery to stabilise the fracture. So one approach is to cut open the fracture and place a plate on the bone, bring all the fragments into their right position. So that's called reducing the fracture. So they reduce the fracture into the right position. Another way is to put a rod down the centre of the bone. So they're called intramedullary devices. You can see with that it's permanent, right? You can't remove that after it's put in. So, but it does add a lot of strength to the bone. Plates, they're usually. A surgeon usually prefers to leave them in unless there's complications. So they could get the tissue rubbing and it's causing soft tissue to get inflamed, so then they may take those out. Casts. The other approach is external fixators. So where you have these screws that come out through the skin to a frame that holds the bone in place. They have some advantages compared to these other techniques, but of obvious disadvantages that the patient can't actually do anything whilst it's attached to them, or their functionality is limited. So design principles, the fixation system must be sufficiently strong and stiff. I mean, obviously we don't want it to break. Provide adequate support. Must be compatible. So it's just like with the joint replacements. But one key point that is considered with these is tunable properties. So as the fracture heals, so we want to change the properties. So right when the bone is fractured, we don't want it to carry any load. We want the plates or the external fixators to carry all the load. But then as the bone starts to heal, we want to offload some of that load through the fixator to the bone, because load on the bone stimulates bone growth. So that's the really neat thing with the external fixators. You can reduce how much support it's providing as the bone heals and takes more load. So the healing process, when a bone's fractured, a hematoma forms over it. Once that's essentially contained, you end up with these vascularization, so where all the blood vessels cross the fracture line. So once that has happened, a callus forms around the entire, around the fracture, and then once you have the blood vessels, you start getting new bone growing in that space. And then as that bone gets loaded, it remodels and optimises its structure. So then it takes on more and more load, remodels, and then eventually it can carry as much load as the existing bone. So that's the ideal sort of target for the healing process. So just to describe that again, you have at the start an inflammatory phase, callus formation. So yeah, I didn't say, the callus forms right at the start. If you don't have a callus form, it's not going to heal. So callus formation, proliferation, bony bridging, which has to happen with the blood vessels crossing the joint. Callus consolidation, so it starts to absorb the callus, remodels, and then heals. So with the different types of fixators, right, no fixation, compared all the way up to the most rigid plate, you get differences in the size of this callus. So the more, if you don't have any fixation around the fracture, you may not get any callus, or if you do, it's going to be huge. And then in the end, it may not ever heal properly. So as you go along this axis, you have more and more rigid types of fixation, and the callus volume is reduced. So for us as engineers, how do we design these fracture fixations? So a lot of the designs can be assessed with composite beam theory. Have you guys done any beam theory previous years? Yeah? Some? So an extension to that, so when you normally do beam theory, classical beam theory, you just have one material, but you can extend it to multiple materials. So to give an example of that, I was just going to go through an intermedullary rod. So that's the case where you have a rod going through the centre of the bone. Oh, so that's the question. Okay, so this bone, a humerus, I think, has a rod placed through the middle to stabilise this fracture, right? So if you look at the cross-section, you have in the centre the intermedullary cavity where there's no bone, then you have your rod, then you have the bone on the outside. So they each have different moduli, so 20 gigapascals for the bone, shear modulus of 3.3. The rod, so we'll try stainless steel initially. Well, I mean, you could change this for different materials. So I guess the point is with this is it's a relatively simple geometry, and we can do analytical calculations to assess the design. So then the question is, what is the bending and torsional stiffness and strength of the bone and rod for a solid rod or a split rod? So you might have this rod sometimes has a split in the middle, which can be put in to allow it to be bent and formed to go down the canal, right? So it's a more flexible design. So the question is, by putting that split in there, how much does it change the stiffness and strength of the construct, the bone plus the implant? So for a normal beam, the compressive bending and torsional stiffness, K, is calculated. So for compression, it's the modulus times area, right? For bending, it's the modulus times second moment of area. And for torsion, it's the shear modulus times by the polar moment of inertia. So have you come across the second moment of area before? Yes? Glad to hear that. So just as a reviser, which of these two cross sections would be easier to bend? If we took that cross section and tried to bend it, which would be stiffer or harder to bend? They've both got the same cross-sectional area, but one would be harder to bend. Hands up if you think that one. Yeah, most people do. The reason being is it has more material further from its bending axis that resists that it gets more leverage. So the second moment of area basically describes how the material is distributed. So this shape would have a higher second moment of area as compared to this one. Therefore, it'd be harder to bend. Now for composite beam theory, it's where we have two different materials in the cross-section. It's relatively straightforward. You just add the contribution of each component. So for the compressive stiffness, you just add the stiffness of the rod plus the stiffness of the bone, and likewise for the other types. So for a circular section, the second moment of area, I, is calculated as these formulas, and the polar moment of inertia is calculated as that. And for a split cylinder, we can estimate its second moment of area with this formula. So it's got a lower value. You can see this has r to the 4, but it's just as r. So we're only looking at bending and torsional stiffness. So the bending stiffness of the construct, so it's the sum of E, I for each component. So E bone, I bone. So for the bone we had 20 gigapascal. So that's, I find it easiest to just always work in megapascal. So megapascal and millimetres is a consistent unit. So the modulus convert to megapascal, 20 megapascal times by that formula, pi on 4. Now we have, we don't have a circle, right? So this formula for second moment of area is for a circle, but we have a tube of the bone. So this is the bone on the outside. So to calculate it for a tube, you just do the outer diameter, its second moment of inertia, subtract the inner diameter. So the 18 subtract might be a mistake because it should be R. Yeah, that should be. Oh no, yes, sorry, 36, yeah. So 36 divided by 2. 18 to the 4, which is the outer diameter's second moment of area, subtract the inner diameter, the 10. So you get that value. And then for the rod, same thing again. It has it's a tube, so you have the outer diameter subtract the inner diameter, and we get this value, add them together, and that's the bending stiffness. Is that clear? So what about the split? Yeah, the split where we don't have any little cross section in there. How would we calculate that? So the question is, would having a split through the centre of the rod make it weaker in bending? Or would it be the same? So the answer is it's the same actually. for small deformation. If it was very large deformation, the split would open it up. But for small deformation, which all these beam bending calculations based on, having a split doesn't actually change its bending stiffness. But for torsion, it changes things. So when you twist, that split allows it to give a lot more. So following the same calculations, basically, we have the for the bone, it's torsional stiffness. For the rod, now for the rod, it's G, the shear modulus times by its polar moment of inertia, right? I only gave the its modulus, but you calculate shear modulus from that formula there. So modulus divided by, use this with the Poisson's ratio. So you can calculate shear modulus if you have its elastic modulus. And then you get, so add those together and you get the torsional stiffness of the intact rod, so no split. And then if we put it into the formula on the previous, so this formula here, where we have for a split, we end up with its the rod's torsional stiffness is 1.5E6 compared to 395. So putting that split in it's made it so much weaker. Right? Okay, so this is another example. I'm going to go on the board. So what we have here is a forearm where the radius has a fracture in it and it has a plate put on it, right? So the question is, if the maximum force that the biceps muscles, so the muscles that flex the forearm, if the maximum force they can generate is 600 newtons, what is the maximum bending and shear stress of the plate? Because if we get that, we can compare it to its yield strength and figure out if the plate is going to fail or not. And one assumption here is that we're just going to assume that the ulna doesn't carry any load. So the radius, you have two bones right in your forearm, radius and ulna. The radius is usually the one that breaks. It has it essentially carries a lot more of the load. So we're just going to assume, for argument's sake, that the ulna is not giving any contribution. Okay, so first of all, if you have a problem like this, what's the first thing you do? If you want to figure out what all the forces are being applied to the system. Draw a free, If I make a mistake, please jump in and tell me, okay? Because otherwise I'll just keep going. So we have the biceps force, F biceps, 60 degrees. I'm going to put a coordinate system based at the elbow joint. X, Y. So we've essentially got the bone in two parts. On the plate. mass at the end. M. And what type of joint is this? This is like, as in, is it a fully supported joint, hinge joint, hinge joint, F? Meaning that there's a force that way, Ry, force that way, Rx. Alright, so we need to calculate bending stiffness, bending stress in the plate. We need to know what bending moments are applied to the plate. Okay? So to do that, we need to resolve all the forces and moments in this system. So, and we said also the force of the biceps is 600 newtons. Right, so the first thing we do, solve this. Sum of forces, so we'll do the x direction. Sum of forces in the x. 0 equals Rx. Subtract F cos or sine F biceps cos of 60. So Rx equals 600 cos 60. What's cos of 60? 0.5. So 300 newtons. Alright, so then sum of forces in the y direction. So 0 equals Ry. Subtract m plus F biceps sine 60. So that, if you put the 600 in there, you'll get m take Ry equals 519.6. Okay, what's the last bit? Sum of moments. Yep. Sum of moments. At when would be the best point to take your moments about? Where would be a logical spot to do it? Anyone? The joint would. So we'll put it at elbow. Zero equals. So F biceps sine 60 times by its lever arm, 3 centimetres. So I said before I like to work in millimetres. 6 times 30. And is that a positive or negative moment? Positive or negative? Positive. Subtract m times by its lever arm, because that's acting straight down. M is 30, so 300. Right, and that's clockwise, so negative. Solving for M, you get M equals 52 newtons. So, if we divide by 9.8, just to see how much mass it's lifting, that comes to 5.3 kilogram. So, it's interesting, right, that if you generate 600 newtons of force at your forearm, all you lift is 5 kilo. The point is also, this isn't just one muscle, it's going to be 3 muscles actually that would do that in reality. So 200 newtons per muscle, that's sort of realistic. Okay, so we have the mass, so we can put that back in down here, so substitute into here, and we get Ry equals negative 467.6 newtons. Okay, so we now know the forces. Now we can calculate what is the bending moment applied to this. Now we know that the load, as in stress, will be shared at these locations, right? Whereas this region here, all the load's going to go through that cross section. So that's where the stress is going to be the largest on that plate. So what we do is calculate, if we call this fracture line or something. So to calculate the maximum stress, we just need to calculate the maximum bending, or the bending moment on that plane. Okay, so to calculate that, we just we do a cut and solve for the internal forces on bending moment. Okay, so the bending moment fracture. So draw again a free body diagram. Now I'm going to call this direction X dash. Have the mass. Now, what are the internal forces of that? Oh, sorry, we're looking at the plate as well. So, at this, we've cut it here, so what's the internal forces that are going through that plate? There'll be a, what? If you imagine this plate, we've just cut it in half. It's in equilibrium because it's not falling. What forces would be inside that plate keeping it in equilibrium? Shear force, yep. So shear force like that, call that V. And a moment. Call that MV. So some forces in the X are unknown, so some forces in the Y. 0 equals V, take M, so V equals M, which is 52 Newton. Sum of moments at cut. 0 equals so MB, that's negative, so negative MB. And M is also creating clockwise moments, so negative M times, you put X, but we know that cut, where it is, so it's 15, so 150 mil. So MB equals negative 780 Newton millimeters. So that's saying that that direction's in the wrong direction, so it's because it's negative, so it's a bending moment that way, as in it's bending the plate like that. So at that plate, the top surface is in tension, the bottom surface is in compression. Okay. Right, so that's all well and good. We know the bending moment, we know the shear force. Alright, so what's so now we want stress, so bending stress. Bending stress is sigma equals m n1 my on phi. You seen that before? Has anyone seen that before at all? Take that as a no. What are you seeing now? It's a relatively simple formula to use though, because you know this second moment of inertia I was talking about before. You seen that everybody's seen that before. So what that is saying that the stress in a cross section, the bending stress. So let's look at our cross section is equal to the bending moment. So I said that the bending moment's like this, 7800 Newton millimeters. Bending stress multiplied by y. So y is the distance from the neutral axis divided by I. So that's what that's saying is the bending stress at the centre is 0, and then as you go away from that axis, it increases. So what we find is the stress looks like this. So for that plate, the top is being stressed in tension, and the bottom half is being compressed. Does that make sense? Okay, so the maximum stress then will be at both different directions, but at the top surface and bottom surface. Okay, so plugging into that formula equals m 7800 times by y, so that's half the thickness, so 4 mil, divided by I. Now I, for a rectangular cross section, is BH cubed on 12. So B. So what would B be in this case? So you have a rectangular cross section there. Which one's B? The 8 or the 20? 20. So the way of thinking of it is, because you can calculate I in different directions, right? We're calculating for bending like this, so the cubed term is sort of weighting any dimension in that vertical direction. Because if that was taller, we'd have more bending resistance. Okay? So the cubed term is giving more bending resistance to any material in the vertical direction. So that's one way to do it. So the 8 cubed by 12 equals 853.3 millimetres to the, what units? Millimetres to the 4. So you can plug that in here, 853.3, which equals 36.6 megapascal. Now, if this plate was made from basically any material, would yielding be a problem? Yes or no? Is a bending stress of that much likely to yield a metal plate, say if it was aluminium or steel? No. So the yield strength for aluminium alloys is around, say, 300 megapascal. So, and steel's even higher. So yielding's not a problem. I'm not going to go through the shear stress because I think we might run out of time if I do. But I'll put these solutions on the website so you can see how to do that. Any questions with that at all? The point with this is that for a relatively simple cross-section we can do hand calculations, and by doing a free body diagram we gain sort of some understanding of the loads in the system. I think it's interesting. Yeah.
Sorry, I have a question.
Yeah.
For the one up above with the 2 cylinders, one each other.
The 2 cylinder. Yeah.
So for the modulus times inertia, is that why is that 18 multiplied by 2 to the 4 minus 2 to the 4?
Yeah. So what's that formula? So for a circle, right, I equals pi on 4 times r to the 4, right? But we don't have a circle, we have a tube. So what you can do is you say that inner circle is negative inertia or negative second motor variant. So then you can put that I equals pi on 4 r outside, subtract pi on 4 r inside. Yeah, do I make a mistake or something?
Isn't like 18 is the diameter and 10 is the radius? So
No. So see, that's for the bone, right? So the bone is the outer one. So that's got an outer diameter of 36 and an inner diameter of 10. Yeah. Yeah, but as I was saying, for relatively simple cross sections, and for bones, if you just assume it is like a cylinder, you can do some, you can get some sort of estimates on your design, what's reasonable, because quite often, from experience, when these plates get chosen, no one does any calculations. They just go, oh, 6 millimetres thickness is good. Yeah, seems reasonable. But you know, as an engineer, the surgeon might come to the engineer and go, "What do you think?" You don't have time to be going and running a simulation. So with this, just drawing a free body diagram, get what your moments and forces are. You can make a few estimates. And from that we see we've got a massive, for 8 millimetre thick plate, we've got a massive amount of redundancy. It's way stronger than it needs to be. All right, so analysing hip and knee prostheses, how do we do that? Because these were for fracture fixation plates. You can do composite beam theory. So this here was the composite beam theory. So you have your implant, you have, in this case, you have the cement going around it. This is a hip replacement, right? And then outside that you have the bone. So again, you've got this 3 different materials, right? So then you can do that same calculation. Calculate what stiffness is. If you had a force like at J, you can, using the free body diagram, you could calculate your moment at section X and then calculate the bending stiffness or the bending stress. Okay. But this technique only works really where there's uniform geometries. So more complex techniques are needed for other regions. So what about stresses and things up here, right? In the end, you need to use finite element analysis. Some other techniques. So there has been analytical solutions done for this sort of geometry. In my mind, once you get to sort of non sort of uniform cross sections, you're best to go to finite element analysis. The beauty of the finite element analysis is you can incorporate all the different, I guess, non-ideal features. So non-uniform material, bone isn't just a constant stiffness. It actually varies based on the density, the geometry. But I think I mentioned last time that they're very time-consuming setup. So usually the finite element analysis is only done for, like, say, an implant that they're going to then go and make thousands of them. If it's just sort of a one-off implant, it's usually not done. They just say, oh, it's similar to previous designs, therefore good. So it's something that needs to be sort of improved as we go forward. How can we analyse things, finite element analysis, quickly? And we don't have an answer yet. Okay, so that's all talking about the bending, stiffness and strength. But what about the articulating surfaces? It's kind of different. That's all about contact stress. So the more contact stress, the more material that can get abraded off. So we need to analyse what is the contact stress. Because, yeah, as I was saying, it can get abraded off. Anything that gets abraded off leads to more stress, and then those little particles can cause infection, osteolysis inside the joint. So that's more or less just what I said. Another time you can also get debris is when you might have some, like say a screw scratches the surface or something like that, or see how you have a ball and socket joint. Sometimes that ball can actually grind against the edge of the socket, right? So if that happens, that's really bad. Okay. So for articulating surfaces, we normally assume the metal deformation is negligible. It's all about the polyethylene. What's the stress of the polyethylene? So we can do some analytical calculations again, where you have polyethylene being indented by a rigid indenter. So this is more for a hip replacement. So you have a socket, which is your polyethylene, being compressed by an indenter. And there's 2 types of contact stress. There's normal stress, right? So as you push on that, there's a force, a stress acting against the indenter, and there's a tangential component. So as it tries to slide, there's some stress in that direction as well. Normal stresses produce both compression and tension stress in the polyethylene. Okay, so talking about contact stress, in the knees the failure is mostly from pitting. So there's the image there showing what pitting looks like, where cracks propagate from the surface of the polyethylene. So contacts, you get some cracks on the surface and they propagate down, and then they start getting carved out. Whereas in the hips, abrasive wear. So abrasive wears just get basically that where it's trying to slide out of position. So in general, lower contact stress is good. Okay, that's the thing to take away from it. A lower contact stress in your joint is better. So as engineers, we tend to try and design these to minimise our contact stress. What's contact stress affected by? It's affected by your loads, which we usually can't do much about. The conformity of the two articulating surfaces. So if you imagine having, say you have a polyethylene socket for your hip replacement, and you have the ball of your prosthesis is really small compared to really large. That makes a difference in your stress. How thick the polyethylene is and the polyethylene mechanical properties. So how do we determine contact stress? We can do a Hertzian analysis. So there are analytical solutions. The other way is finite element analysis. The thing is with finite element analysis, it's very hard to get contact working reliably. You get predictions of contact stress, but you don't always believe what you get. So the analytical calculations are reasonably reliable. Okay, so this is just an example of how that works. So if you have a ball, which in our case for the hip replacement, that's the ball of the femoral head, right? And then you have a dish, which is the socket. So that's the polyethylene. You can calculate from Hertzian contact theory, which I wouldn't ever try and go into in the lecture. It's pretty involved. But you can calculate the maximum pressure in the polyethylene is that formula, where A is the radius of the contact area. So you can see here, in this picture, you have this small little area that's where all the contact is. Right? So that's where all the contact stress is going to be. So the contact area is calculated from these formulas. CG, CM, they're a function of the geometry and the material. You have Poisson's ratios in there and modulus. Is that clear? Any questions on that? Am I losing you at the moment? Bottom line is that if you had a ball contacting against a dish, you can calculate your contact pressure from this formula. Okay, it's an analytical solution. Okay, and it's a similar geometry to our hip replacement. So as an example, say we have a hip implant, polyethylene cup, metal head. They have these two different diameters. So the diameter of the head is smaller than the diameter of the cup. The polyethylene has a modulus of 1 gigapascal, so it's pretty soft. Now, if our load going through our joint was 3 kilonewtons, calculate the difference in the maximum pressure, so this formula, the difference in that maximum pressure for two different materials of our implant. So chromium cobalt has a Young's modulus of 200 gigapascal, and titanium alloy, which has a Young's modulus of 100 gigapascal. So a material that's double the stiffness, what effect does that have on the contact pressure? So I'm just going to rush through this because I've run out of time. So we put in those formulas, and in the end we'll get the contact area of the polyethylene for the chromium cobalt, 4.69 millimetres. The area is that should be millimetres squared, I think. And maximum pressure of 65.1 megapascal. Now let's repeat that for the titanium. So the titanium that's a softer material. we see that it's made hardly any difference at all. So the stiffness of the actual implant, because it's orders of magnitude greater than the polyethylene, it doesn't matter, right? It's just like any stiff material will have a similar contact pressure. But what about if we change the polyethylene to metal on metal? So if we repeat these calculations for titanium and chromium cobalt, but we have the socket, instead of polyethylene, we use the same material. So what we find is for chromium cobalt contacting chromium cobalt, the area is much lower and the maximum pressure is massive. So we've got a pressure of 2,000 megapascal, which is enough to cause yielding easily. I'm not going to go through the titanium. I think you get a similar answer. Okay, so that's sort of shows why you don't usually do metal on metal contact. All right, so that's basically it. I just wanted to show one last thing. Just some of the research that we're involved with in our department, just to sort of give you an idea of it. So, I mean, we do some of these, a lot of finite element analysis, but also combined with 3D printing. So, this here, I spoke about it on Wednesday, the reverse shoulder implant. So we've done some analysis on that, looking at the stress. 3D printed tooth implants. So this here shows the standard type of tooth implant. There might be someone even here that has one of those. We're looking at 3D printing those tooth implants, because if you 3D print it, you can have the exact geometry matching the tooth that was pulled out. Another one that we've been doing work on recently are these osseo-integrated implants. So this is where you have an amputee. They've had their they've had their leg cut off. Usual way to allow them to walk again are sockets, right? So pressure-fitted sockets that get strapped onto the patient. But they have a lot of problems where the socket rubs against the bone or the stump, all the skin and everything. So it rubs, sweats. So it has a lot of issues. So the solution that has been looked at more and more recently is to have an implant put up into the femur that comes out through the skin, and then by doing that you connect your the prosthetic limb, the lower limb, to that implant. So by doing that, you have now a direct connection to the skeleton, right? You don't have this interface where you have the socket rubbing against the skin. You have basically all the load going from the foot straight up into the skeleton. So yeah, we did analysis of that, looking at all the muscles and stresses on the bone and implant. Another one's 3D printed fracture plates. So where instead of having a surgeon shape the plate to the patient, you can actually 3D print the fracture plate. And lastly, work on cartilage. So this is showing a piece of a cylinder of cartilage, what it looks like when it gets compressed. All right, so that's about it. Thank you everyone for listening, and if you have any questions, just come ask me.